redesigned the backend to quickly handle millions of reads and writes. Adopt the right backend strategy for your microservice to handle huge loads of reads and writes. By Matteo Pampana. So let's see. Basically, he is going to describe, as it seems, to how he redesigned a backend. I wonder how many requests it could handle before the redesign, and after the redesign, it would handle millions of reads and writes. I estimate with multiple services. Also, it doesn't say for how many seconds. I mean, millions per how much? Per day, per hour? But let's see. I'm sure the article will describe it. So I was at my desk on a lazy Monday morning. Suddenly an alert appeared on my screen. Our endpoint to show a user's profile info was taking a lot of time to process the request. Okay, so he got basically an alert, or he sees that it's taking a lot of time to process request. I was responsible for that part of the system. I had to do something quickly. Customers are the most important part of a company. If the APIs are not efficient, they will experience waiting. Waiting means ugly spinners, rage, and quitting your application. You may lose some of your active users, you decrease the returns of the company. Yeah, I think it says the general notion is that a couple of 100s of milliseconds and users already perceive. So less than 100 milliseconds, user might not perceive the difference, but more than 100 milliseconds, 200, 300, 400, user will begin perceiving this latency. So the user experience UX, even for a nerdy backend engineer, should be a polar star of your daily activities. Yes, you should see the graphs. Basically, the best practice is to on a daily basis to watch the graph, to know your latencies and see them on the monitoring. I did not want an angry customer screaming on my shoulder, so I drank my coffee and started thinking about solving this issue. Okay, but what is the issue? Let's see. I was working with microservices architecture that ran on Kubernetes cluster. For sure, we could have scaled horizontally, and increasing the number of pods. Could this have solved the problem? In some cases, yes. In some cases, not. Could this have been sufficient? Maybe, maybe not. Totally correct. Sometimes the service is just not efficient, and you need to invest time in increasing performance. Usually, the basic performance gains we gain initially are huge. So the UI, the profile page, is calling the service, the profile service, which is contacting the DB. We see here multiple points of latency. The DB could be slow. If the DB is not in the same region as the service, this could also be a reason. So the communication manner with the DB, the number of connections, there are a lot of causes. In fact, you can add more pods, but doing so increases the number of connections exactly you have to establish with your database. Your database instance in turn does have its own limits and may not be able to handle all the requests. When something is not unlimited, a scheduling policy can occur. Some processes may experience waiting times, thus increasing the response times of your API. I needed an alternative. I started looking on our beautiful dashboard for the user profile. Let's see the dashboard. We see load time vs bounce rate. What is this? The bounce rate is the number of users that are bouncing away from the page. We see that the bounce rate is decreasing, median page load time. Median page load time is 2 seconds. That is huge. That is huge. And the bounce rate is increasing. Here is like the point where it's actually increases. Start render versus bounce date. Okay, so we see here a median of 2 seconds. That is pretty big, right? The graphs were talking out loud. We were experiencing huge load on the endpoint that was creating new profiles. Huge load. What is the load here? What is the load? Sessions. Lot of sessions. Okay, it's not that clear. Let's see. The graphs were, instead, the endpoint that was retrieving the profile info had nothing unusual. The traffic was the same as the day before, its response was not. I scratched my head. The creation endpoint was having a peak in traffic, and this was causing decreasing performance in our reads. Yes, I knew to tackle this issue. CQRS. We are getting into complex topics. I wonder if we could make this simpler before we get into CQRS. Command query responsibility segregation. There is a pattern known as CQRS, command query responsibility segregation. This pattern is not rocket science. In this jargon, a command module is responsible for creating and uploading a piece of data. So far, sound good. A query module is responsible for reading that piece of data. Okay, so it's splitting the writes from the reads, and there is a command query. The pattern is not rocket science. In this jargon, a command module is responsible for creating and uploading. So here the command is creating and updating a piece of data, or telling to update, and the query is responsible for reading. I wonder what it's just standard best practice to separate reads from writes. Let's see. Long story short, the CQRS pattern tells you must separate module that writes something from the module that reads something. Yeah, totally makes sense, even without CQRS. In this case, we were mixing up on the backend side writes and reads. Oh, so, okay. This can explain a lot of things. Some databases are efficient for read, some are efficient for write. It depends really on your architecture. If you're contacting the write node needs to make sure things are written. So, and the write sometimes is a specific single node, while reads can be 100 nodes. It depends if you want strict consistency or not. So yeah, separating reads and writes, of course. A peak in the traffic that request writes on the database, which is typically slower than the reads, has caused the attrition of the reads endpoint response time simply because it had to wait an unexpected amount of writes. Yeah. Never mix. In general, we don't mix writes and reads. I decided to apply the CQRS. Even without CQRS, I'm just relating the reads and writes. CQRS pattern to backend architecture. Firstly, I created a database replica. This is very easy operation to perform if you are running on a cloud provider like AWS. They managed to create and maintain a replica of your DB instance in a few clicks. So I transformed my backend architecture into something like this. Yeah, so here he has the replica which does the reads, and all the writes goes to the main DB. So far makes sense. Usually also you don't need the reads to be the latest data. If yes, then these are specific cases that you can handle. As you can see at this point, my service was still represented as a little monolith, but the writes operation were not interfering anymore with the reads. The tricky part here is that sync arrow on the right. It is not trivial to sync multiple storage systems. There are many techniques that can be used to achieve it. I will tell you about my experience with these different techniques in a different article. For now, let's move on with our story. Secondly, I split the profile service into two services. You can guess the names of the modules: profile command service and profile reads query service. The profile command service, I usually just split to write and read. The profile command service was responsible for creating and updating a user profile info. The profile query service for retrieving it. So the backend architecture has become something like this. Profile page from the UI going to a proxy, separating to profile command which does the writes to the main DB, and then profile query which does the read from the replica. In this picture I decided to show also the reverse proxy to route the UI. Makes sense to mention here what is a reverse proxy. Usually with reverse proxy, it's like you are looking at the traffic coming at you and you are the reverse proxy splitting the traffic, while with the proxy, you know your target and you are going to the target service. So this is the difference. In general, we can discuss it more in general between proxy and reverse proxy. In proxy, you know the target. You are going to the proxy because you know you want to get to the target. In this picture, I decided to show also the reverse proxy route request to the correct service, but this was present even in the previous one since we were talking about microservice architecture. This separation allowed me to scale the two services differently. Tip: you can use an open source toolchain like Bit for splitting profile command and query services. I wouldn't bother. Into reusable independent components that can be shared across multiple microservices. This would help to further reduce the complexity of the architecture and enable you to focus on building and scaling specific functionalities of the microservices. Wait. Okay. Increasing traffic on the creation updates of the profile info will be handled automatically, scaling up. Okay, we got the idea. I can sum it up in 2 words: separate to reads and separate to writes. That's all. The response time went back to normal. Now our users are happier ever, and we have never faced a problem since this issue. Conclusion. I learned how to deal with peaks in traffic that in turn involve operations on storage systems. I wanted to share with you how simple the CQRS command query responsibility segregation, or as I call it, separate the read and writes pattern is as a concept, and how powerful it is when applied to the design of backend architecture. In fact, the interesting stuff is not really the CQRS pattern itself, but the architectural decision that can be made thinking about it. I was, and I currently am, amazed by the impact of this simple concept had on my backend performance. Okay, so that's it. So this was this article. If you want to actually read it, it is called How I Redesigned, right? How I Redesigned the Backend to Quickly Handle Millions of Reads and Writes by Matteo Pampana.